Okay, we're going to look at the proof for something called the tan-chord theorem. First, the tan-chord theorem, what does it mean? Well, let's take a look here. It means you see this angle here between, this is the tangent, and here's the chord BD. That B2 is the angle between the tangent and the chord. It always equals the angle that's in the alternate segment right up here at the top that subtends that same chord, that opens up to that same chord. It's like if this was a sail, you'd be hanging on to this little piece here, the chord. The top of the sail is what the angle is equal. B2 right there equals E2 right there. That's called the tan-chord theorem. Now, how do you prove it? Well, if you've got a picture like this, you get a mark if you draw a dotted line between the center. That's your construction that you're going to have to do. You draw a diameter BOF, and then you join this little thing from E to F. They give you a mark just for that. Well, we know that the tangent is perpendicular to the radius, so we know that B1 plus B2 is 90 degrees. But hey, we know that E1 plus E2, it opens up to a diameter. It's 90 degrees. Well, the only way, we know that B1 equals E1. Isn't that true? B1 equals E1 because it opens up to FD, angles in the same segment. Okay, so if B1 equals E1, then we have our proof. That means B2 always has to equal E2. So we just proved the tan-chord theorem. Remember, this is one way to do it. I think it's the nicest way I've seen. Just draw a line straight through the center, make a diameter, because you're going to use that diameter thing, connect this thing, and the big trick is, just remember this big trick. The tangent perpendicular to the radius is the same as the 90 degrees. It opens up to a semicircle, to the diameter. And then the last two things, you go, oh yeah, B1 equals E1 because it opens up to this chord, angles in the same segment. FD subtends equal angles. It should be angles in the same segment. That's what I would say there. But anyways, that's it.